Okay, so in this video, I want to pause from our examples where we were computing Fourier series and take a moment to consider where these formulas for the a sub 0, a sub k's, and b sub k's come from. So in order to derive those formulas, we're going to rely on some of these integrals that I've listed here. So treat these as facts. I mean, we could go through and actually verify these for each of these, but whoops, this should be a 2 pi a. So I just want to be able to kind of reference these. So I'll scroll back up to these from time to time. And to think about what we're trying to prove here, I'm starting with the assumption that I can, in fact, represent my function as equivalent to a Fourier series, like we said before. So suppose that f of x, we know we can express it as a sub 0 plus the sum from k equals 1 to infinity of a sub k cosine kx plus the sum from k equals 1 to infinity of b sub k sine of kx. So we know the formulas that we should get, but let's see why that's true. So from here on out, I'm going to make this is my starting point. So with this assumption, let's first consider how we could find a sub 0. So to start with, what I'm going to do is start with the red box, and if we're assuming that that equation holds true, if we do the same thing to both sides, then those should still be equivalent. So let's integrate both sides of the expression in the red box from minus pi to pi. That would tell me that the integral from minus pi to pi of f of x should equal the integral of everything on the right side, which I'm going to break up as 3 different integrals. So the integral from minus pi to pi of a sub 0 plus the integral from minus pi to pi of the sum from 1 to infinity a sub k cosine kx plus the integral from minus pi to pi of that last sum. Now, much like we've seen with power series, I'll point out that I'm integrating a series that has terms involving x, my integration variable. And the way that we dealt with that with power series is we call that really term-by-term integration, which effectively we were swapping the role of the sigma notation and the integral. I'm going to take advantage of the same thing here. So I still have this first integral as it is, but then I'm going to say that that's plus the sum from k equals 1 to infinity of a sub k, the integral from minus pi to pi, of cosine kx plus the sum from k equals 1 to infinity of b sub k, integral from minus pi to pi of sine kx. And again, one other thing that I should address is I brought the a sub k's and b sub k's out front of the integral because those were constant with respect to x. So now what I want to look back at are a few things. So in here, I have the integral from minus pi to pi of cosine, and I have the integral from minus pi to pi of sine. And of course, the argument there is kx in both cases. But if you look at my integral number 2 and my integral number 3, both of those integrals should evaluate to 0. And really, this means for any of the k's, 1, 2, 3, etc. So we have a sum where we're taking our a sub k's and each of them is multiplied by 0. And we have a sum where we're taking our b sub k's and each of those is multiplied by 0. So effectively, the sums are summing 0 again and again. And so those are going to be 0. So we're left with an equation. So we have that the integral from minus pi to pi of f of x must equal the only thing that's left on the right-hand side, the integral from minus pi to pi of a constant. And of course, we don't really need integral number 1 to tell us this. Think of this as just the area of a rectangle whose height is a sub 0 and width is pi minus negative pi, or 2 pi. So if we're equating these two things, if I divide both sides by 2 pi, I'm going to get the formula for a sub 0. And of course, this is exactly the formula we wrote before. So we see that by making the assumption that we could express the 2 pi periodic function f of x as we did, then the only way those two sides could be equivalent for all x is if we end up defining a sub 0 as we have it here. And this is much like the way that we ended up kind of coming up with the derivation for Taylor polynomials and therefore Taylor series for what that coefficient should look like. We can use a similar process to find either the a sub k's or the b sub k's. And because there's going to be too many variables involved, I'm just going to pick a particular k value in some sense. So let's go back up to the red box that we have there. And so I'm going to start over, and we have those two sides that are equivalent. And one thing I want to point out is that if we multiply both sides of the boxed equation by the same function, in this case cosine of 3x, then those two sides should be equal. So that tells me that f of x times cosine of 3x should equal a sub 0 times cosine of 3x plus the sum from k equals 1 to infinity of ak cosine kx times cosine 3x plus the sum from k equals 1 to infinity of b sub k sine kx times cosine 3x. So again, that's doing the same thing to both sides of the expression in the red box. And then now, with our new equation that I have here, let's integrate both sides with from minus pi to pi. So that tells me the integral from minus pi to pi of f of x times cosine of 3x should be equal to the integral from minus pi to pi of the right-hand side. And again, I'm going to take advantage of the fact of a few things here. I can break that up into 3 integrals, and I'm also going to skip to the step that I did here above, where I'm going to say that integrating that sum, I'm going to instead represent as the sum of the integrals. So that would leave me with a sub 0, the integral from minus pi to pi of cosine 3x, plus the sum from k equals 1 to infinity of a sub k times the integral from minus pi to pi of cosine kx times cosine 3x, plus, which I'll put it down here, the sum from k equals 1 to infinity of b sub k times the integral from minus pi to pi of sine of kx times cosine of 3x. So what I'd like to do here is, again, look back at some of my integrals that are given in the beginning. So first of all, the integral of cosine 3x, that is just integral number 3 above, where m is 3. And we know that that goes to 0. So this constant term here is end up multiplied by 0. Then I have the integral of sine kx times cosine 3x. That's going to be equation number 6. So I have a specific value for n, 3 in this case, and we just have a sine of kx. What integral number 6 is telling us is that for any whole numbers n and m, that is going to evaluate to 0. So we once again have this infinite sum where every single b sub k term is multiplied by 0, which means that that whole sum is going to be 0. So we're now left with the, let me maybe give this a different color. We're now left with just this middle term, and in particular, we have to focus on integrals of cosine times cosine. And that brings me to this 8th one here. And notice that that depends. If we're multiplying two cosine functions together that are identical, then that integral evaluates to pi. But if the arguments of the cosine differ, then that evaluates to 0. So let's think about what the consequences are for that. Looking at my next page here, what that tells me is that, so going to the next page. So what we have left is, on the left-hand side, the integral from minus pi to pi of f times cosine of 3x. And that is equal to that second summation. And what I want to think about is what each coefficient a sub k is multiplied by. So if I consider a1, that's the integral of cosine 1x times cosine 3x. because 1 does not equal to 3, that integral is 0. So a1 would be multiplied by 0. When I look at a2, that sits next to the integral of cosine 2x times cosine 3x. Because 2 does not equal 3, that 8th integral formula tells us that's 0. And when I get to a3, then that sits in front of the integral of cosine 3x times cosine 3x. And we are given in either formula 8 or formula 5 that in that instance, that integral should evaluate to pi. And then when I get to k equals 4, we would get a4 times the integral of cosine 4x times cosine 3x. That integral is 0. Likewise, a5 would be multiplied by 0. And essentially every other coefficient after this would be multiplied by 0 because of that integral formula in number 8. So we really just are left with the only non-zero term, which is a3 times pi. And again, we are equating these, which means that if I want to isolate a3, I can divide both sides by pi, and that gives me a3 is 1 over pi, the integral from minus pi to pi of f of x times cosine of 3x. And of course, this is exactly the formula we wrote down and assumed to be true, and now we see where that comes from. So one thing you can see here is why do we have a 1 over 2 pi for a sub 0, but all of the other coefficients have a 1 over pi? And that really comes from these integral properties that we have above. And then the last thing I want to mention about this is that even though I just found a sub 3, this is a little bit more broadly applicable than might first appear here. So we could swap out 3 for any other positive integer to find, so let's say any other positive integer k, or let's say n, because I'm using k as my summation index, to find a sub n. Also, to find b sub n, we could go through the same process above, but we would replace the step where we multiplied by cosine of nx by sine of nx. So in this last part, I've really demonstrated the way that you could derive the formula for either a sub k or b sub k. The key step was that we first multiplied everything by the function that served as the coefficient for. So a sub 3 was the coefficient in my Fourier series for cosine of 3x, and cosine of 3x was the function I multiplied everything by. So this now kind of gives us some reassurance that these formulas we wrote down didn't really just come out of thin air. These were necessary once we made the assumption that we could in fact find a series approximation of our 2 pi periodic function f of x that consisted of these terms.